Okay, thank you. First, I would like to thank the organizers, and especially Johanna, for organizing this very interesting workshop, and also for giving me the opportunity to talk here. So let me start with an introduction. So the best, as we all know, the best understood holographic duality is between n equals 4 Young-Mills and ADS 5 Kostas 5. But of course, if we want to move to more realistic examples, we would like to understand examples where they're not necessarily conformal and they have less supersymmetry. And this was a goal from the very early days of ADS CFT. And since, let's say, already from 98, there was significant effort devoted to obtain dualities with less supersymmetry and not conformal symmetry. So what I will do today is I will revisit this old problem, and I will discuss how to systematically understand all n equals 1 deformations of n equals 4 Young-Mills that can be studied holographically. And then at the very end, I will focus on the simplest such example, which is the so-called n equals 1 star Young-Mills theory, and see what we can learn from the things that happened between 98 and today. Okay, so this talk will be based on 2 or 3 papers. So the first part will be based on something that, in the paper with my student Stanislav Smith, that should appear sometime soon. And then the second part about the GPPZ will be based on a paper written with these authors plus ongoing work. And I should also mention that there was also another paper on the same topic which appears simultaneously. And you should consult both papers. Okay, so let's start from the beginning. I think this, or before that, let me also say that, especially in the first part, there's a lot of work that happened, in a sense, at the beginning of ADS CFT, and this is going to build on that. In a sense, we're going to collect things we learned 20 years ago and try to see how to systematically understand the problem at work. But there was one thing that we did not know 20 years ago. Everybody expected that type 2B supergravity has a consistent radiation on S5. This has now been proven, and there are also very explicit formulas given in this paper, and this makes possible things that one could not do 20 years ago. And this was one of the reasons that we came back to revisit some of the open issues from 20 years ago. Okay, so let me give now the outline of the talk. So I will start with a little bit a longer introduction, things which should be familiar to the older people in the audience, but perhaps things which kind of the new generation that grew up with entanglement entropy and complexity and all that, they haven't seen so much. Then I will go on to discuss something which is, it is a little bit on the literature, but I think I'll try to make it a bit more precise. So I'll try to see how to go directly from quantum field theory to supergravity, avoiding doing complicated supergravity computations. And he thinks that in the heroic days of ADS CFT, that people were deriving potentials from supergravity with very complicated computations can be understood conceptually very simply by understanding what is happening on the quantum field theory side. And then I will move on to discuss or outline the classification of n equals 1 deformations of n equals 4 Young-Mills that can be understood holographically. And I will finish with discussing the GPPZ solution and its uplift, and then I will conclude. Okay, so let's go from the beginning. So first recall how duality works just in the case of conformal field theories. So what we learned very early on is that half BPS operators of the superconformal field theory correspond to bulk supergravity fields. So now if one is interested in moving to non-conformal cases, there are simple things one can do. So we can start with a duality that involves the CFT, and then we can deform the CFT with one of these operators. And then to describe now this theory, what we do in the bulk description is given in terms of the so-called domain wall spacetime, which is the spacetime of that form. And the fact that we're describing this deformation here is encoded by the boundary conditions that you impose in your bulk field. So in particular, you want this scale, this scale factor here to go like R as we go to infinity, then this becomes ADS, and then the scalar field has this form of asymptotics, and then this quantity over here is the deformation parameter. Now, exactly the same type of spacetimes also describe the case where we have a quantum field theory with condensate. In that case, the only difference is in the asymptotics of the scalar field, which now asymptotes with goes to 0 with this rate. And now this parameter over there has interpretation as the vacuum expectation value of the operator. Okay, that's the main players. Now, before I continue with the construction, let me also remind you the framework of fake supergravity. So if it turns out that we have solutions of that form that have the property that the scalar field here is invertible, then this automatically implies that there is a first-order formulation given by these two equations, where this W here is a so-called fake superpotential. If this would be a truly supersymmetric flow, the W would be the superpotential that comes from supergravity, but here it's defined by the solution itself, and is defined by, this is the scale factor. You use the fact this is invertible. So if you put it here, then you get the superpotential, and then the scalar field satisfies this equation that is also determined by the same superpotential. And it turns out that when you define the superpotential in this form, then it's automatically the case that the potential of VFI can be written in terms of superpotential in this form. So these equations appear in many different ways with many different justifications in the literature. For instance, arise also by using Hamilton-Jacobi theory, also arise in the case of the theory of supersymmetric, but here one can derive this, or some people also view this equation as a differential equation for determining W and so on. Here they just follow from the assumption that the scalar field is invertible, at least locally. Now, why is it important to have it in this form? The reason is that if you have a theory with the potential of that form, then these theories enjoy positive energy theorems, and this has strong implications. In particular, always imply that the solution we're describing here is stable perturbatively, and in many cases also non-perturbatively, namely for fluctuation, for all configurations which asymptote to the same values have higher energy than the one we have been describing, even when they're not close to this one. So in this case, I'm describing the case of one field. There are extensions also for many fields. So of course, I have to solve for phi, and I have to solve for A as well. So it's a system with, let's say, two variables. And the first of the system is given here. There are generalizations for many scalar fields as well. And some of these implications also hold in the main scalar case. Okay, so now, so we want to study this domain wall spacetimes because they describe these deformations, and we have this framework of fake supergravity. So one additional piece of data is a so-called holographic beta function, which is given by this formula in terms of the superpotential. So if you know that superpotential, you also know the beta function. Now suppose you know the beta function from quantum field theory arguments. Now, this is something that could have been done 20 years ago, and I'm not sure why it wasn't done 20 years ago, but it's a very simple exercise to combine these three equations, these two plus that one, and integrate them exactly. And this is the answer. So you can get the superpotential in terms of the beta function as a function of R, and then you can obtain the value of the scalar field given the beta function alone. So from here, we know W. We put it here. We know F. Of course, now we have the assumption that this is invertible. So we invert this, and then we put it here. And then we get the superpotential. And then from here, we get the potential. So from field theory, you go directly to the supergravity potential with only input the beta function. Here again, the summary. So given the beta function, we can obtain the potential. So then the question is, when do we know the beta function exactly? So now the next step would be to discuss this in the most controlled possible case. So now suppose you have an n equals 1 supersymmetric system. Now the oldest of the normalization theorems is that superpotential terms do not normalize. So now suppose we modify the superpotential of our theory by adding a new term where this O hat is a chiral superfield, and this is the corresponding coupling. Then the non-normalization theorem implies that the beta function for this coupling is given by this expression, where d is a space-time dimension, delta is the classical dimension of the F term of this chiral superfield, and in general, they can be anomalous dimensions. So the delta can be corrected quantum mechanically. Okay? So now let's simplify even more the problem and assume that O hat has a protected dimension, which means this is 0. So then in this case, this becomes a very simple differential equation that one can exactly integrate. And then in holography, the normalization group scale is related to the radial variable. So now we know, so for this specific case, in this setup, we know what is the beta function exactly, just from quantum field theory arguments. Okay, so now that we know the beta function, I could just use the formulas I had earlier. And this, now we get the formula for the superpotential and the formula for the potential. Okay. So now we managed to go directly from quantum field theory to supergravity using a rather simple argument. So can we actually realize this? So next step is to realize this explicitly. And this explicit realization, it would be done in the context of n equals 4 spin-Young-Mills and using the half BPS operators. So we know that half BPS operators have no anomalous dimension. And some of these half BPS operators can be considered as F terms from the perspective of an n equals 1 theory. Or in more detail, we can first rewrite n equals 4 theory in n equals 1 language, and then use some of these half BPS operators to deform the theory. Okay, that's what we want to do. So let me now review the first step. So the field content of n equals 4 spin-Young-Mills in terms of n equals 1 multiplets consists of 3 chiral superfields, capital Z sub I, and 1 vector multiplet. And then when you write n equals 4 spin-Young-Mills in n equals 1 language, this breaks this SU4 R symmetry into SU3 cross U1R. And then the action takes the form of the standard n equals 1 Lagrangian. We have a Kähler potential, we have a gauge kinetic term, and a superpotential. In the case of n equals 4, these are given by these simple expressions. Okay, so now if you want to study n equals 1 theories using holography, what we want to do is we want to identify the n equals 1 deformations that involve half BPS operators, because this is what we have at the disposal holographically. So in particular, we need to identify the parts of the half BPS operators that are superpotential terms, the parts which are deformed the gauge kinetic terms, and also D terms deformations. Now for the argument I had earlier, these D terms are not particularly interesting because, of course, D terms do normalize, but the other two do satisfy normalization theorems. At the same time, since we're going to do the classification, we're going to classify all cases because maybe the D terms would be interesting for other purposes. Now, if one has an n equals 1 superconformal theory, now in general, the bottom components of chiral superfields may also condense. And of course, this is one information that we would like to extract holographically as well. So we need to identify holographically, we need to identify which of the components, which of these bottom components sit in high PPS operators of n equals 4 Young-Mills. Okay, so now if you want to get one message from this talk is that we have classified all of these cases. Now in the remaining time of the talk, of course, I cannot give you the entire classification. I'm just going to give you a feeling of how it goes. But we've done all cases. So the case is going to contain a discussion of all cases. So what I'm going to do next, I'm going to indicate how things go. So to do that, first I have to remind you a few things about half BPS operators of n equals 4 Young-Mills. So the superconformal primaries are given by symmetric traceless combinations of the 6 scalar fields of n equals 4 Young-Mills. And then the rest of the half BPS operators are obtained as superconformal descendants. Therefore, we start from the top, and then you act with the n equals 4 supercharges. Now, if you consider the case of only 2 scalars, so this is the lowest multiple, this is the n momentum multiplet, and corresponds to the gauge supergravity. And if one looks for p greater than 2, then we get the Kaluza-Klein modes on the S5. It would be useful to have kind of a picture of how this works. So these multiplets are organized in terms of diamonds. And the generic case is a case where you have the full diamond. This happens from p equals 4 and above. P equals 2 and p equals 3 are special, the shorter multiplets. So here I indicate the multiplet for p equals 2. So in the boxes, I indicate the representation with respect to SU4. And then the small brackets are the space-time quantum numbers. And this is 0, 0. This means it's a scalar. This is a fermion. Here we have a self-dual tensor and a scalar, and so on. So the first step to understand the n equals 1 multiplet is to understand how to go from SU4 into SU3 cross U1. Actually, before we do this, let's so we have these multiplets, and corresponding to these operators, of course, there is a correspondence in supergravity in terms of Kaluza-Klein modes, and these are organized in Kaluza-Klein towers. So here in the bottom, this is the p equals 2. Then p equals 3 is again is a bit longer, but still short. So then for p equals 4, we have the full thing. And then on top of that, they sit all the Kaluza-Klein modes. So all operators are organized into this kind of tower state. So we know exactly how to identify which operator sits where. So next, we need to understand this breaking from SU4 to SU3 cross U1. That's a group theory exercise. So here I've done this for p equals 2. So for example, this 20 prime that was sitting over there, this is broken into a 6 bar, an 8, and a 6 of the SU3. And these numbers here are the U1R quantum numbers, and so on. So now we know how this kind of multiple is decomposed into SU3 cross U1. So next, what we want to do is we want to organize them in terms of n equals 1 multiplets. And this can be done for the entire towers. So here I'm going to just do it schematically. So if we want F terms, so there is a diagrammatic way to do it. So in a sense, this red line here represents an n equals 1 multiplet. So you start from here and you go 2 lines down. And then all chiral multiplets are given by either going diagonally to the left or anti-chiral diagonally to the right. So there is a diagrammatic way to identify all possible n equals 1 multiplets. So now a particular case of interest is a case that gives the deformation, the n equals 1 star super Young-Mills. This corresponds to just adding a specific member of this to the Lagrangian, so it's a symmetric mass term. And that has dimension delta equals 3. So now we can, so this is a case where we should be able to apply the general formula I had earlier. So if you're plugging into the formulas I gave you earlier, this is the superpotential and the potential. And that's precisely the superpotential and the potential, which was worked out by heroic effort by GPPZ 20 years ago. Actually, we repeated that computation, and it took a month to do this to get into this formula. Well, here you get them in a few minutes. Okay. So if you want to do general P, you just start with the general you start with Z to the P, and again you use the same graphical decomposition. So all of these modes originate from Kaluza-Klein modes of the undersymmetric tensor on the S5. And these arguments suggest that there exist massive single scalar consistent truncations of type 2B supergravity with a potential given here. So that's a challenge for the consistent truncation people. And there is also a related consistent truncation with two scalars, which I can explain to people that are interested afterwards. This is very surprising from the perspective of consistent truncations, because these consistent truncations are not controlled by some bosonic group. Their existence originates from a fermionic symmetry, the fact that the specific operators are protected, are superpotential deformations. So it's a different kind of argument for the consistent truncation. Okay, now moving on into the classification. If you're interested in studying gauge the deformations of the gauge kinetic function, then you should look this type of superfields over here. So you start at the top with Z to P minus 2W squared, and you start from here, and this is the deformation. And this deforms the gauge kinetic function by Z to the P plus 2. And if you're interested in D-term deformations, first of all, this appears only when P is greater or equal to 4. So all of this correspond to n equals 1 high derivative terms. And quite intriguingly, all of them are characterized by harmonic functions. So one example of such deformations is the one I gave over here. So this function here is a harmonic function, namely is satisfy box on G equal to 0. And you multiply with W bar square. So this type of term is n equals 1 is a D-term deformation. This type of terms, I'm not sure have been studied in the literature, but they should have some more special properties because they originate from n equals 4 spin-Mills. What about condensates? So first of all, n equals 4 spin-Mills does not have vacua that spontaneously break supersymmetry. But we could first deform the theory to n equals 1, as we discussed earlier. And for example, in the case of n equals 1 star super-Yang-Mills theory, it is well known that there is Gluino condensate given by a formula of this type, where m is the deformation. So in the large Stoft limit, this factor goes to 1. So we just get the deformation. And then the condensate satisfies this equation, which is the analog of beta functions. So then using the same argument I had earlier, but now for the webs, one finds again the superpotential. And again, the superpotential is exactly what it was worked out by GPPZ 20 years ago, now derived directly from quantum field theory. Okay, I only have a very short time, so now let me move to the quickly summarizing the last part. So the GPPZ solution was meant to describe this mass deformation. The solution is explicitly given here. So here, m and sigma are the norms of the complex sources that couple to the deforming operator in the Gaussian bilinear that I described earlier as getting a wave. The solution has a naked singularity, but the solution should be acceptable if this integration constants C2 and C1 are ordered in this fashion, if one uses Gupta's criterion. And the solution, again, was proposed to describe one of the confining vacuum of n equals 1 star. Notice, however, that has a naked singularity. So now in quantum field theory, the sources are complex because these are deformations, either superpotential deformation or a source for a chiral operator. So strictly speaking, one should include the phases for the sources. Secondly, in quantum field theory, we expect this answer. And in gauge gravity duality, we expect such relations to come from regularity conditions. However, there is no choice of integration constant such that the solution is regular in 5 dimensions. There's also a computation that suggests that the spectrum contains a massless state. So perhaps that solution is not dual to a confining vacuum, but is dual to a different one of the Coulomb vacua of n equals 1 star. Finally, there was a proposal in 10 dimensions for the n equals 1 star proposed by Puczynski and Strasser, and one can ask what is the relation between that solution and the GPPZ. So to answer these questions, we wanted to uplift the solution to 10 dimensions because singularities are often resolved when you go to higher dimensions. So we indeed generalize the solution to complex M and sigma, which is needed to describe properly the quantum field theory. It turns out that the phases of M and sigma have a nice geometrical interpretation. So they can be accounted by a combination of rotation in S5, which geometrizes the R symmetry and a rotation of a U1 in the SL2 of type 2B. The 10D metric of the action and the action dilaton agree exactly with the partial uplift of Pilch and Warner. But now we also have all P forms. All P forms are present, but they're all given in terms of elementary functions. So this is a solution that is amenable to further analysis. And we have also included the Mathematica file in the submission. So if you want to play with it, you can just get the mathematical file where you have the solution already there. So what about the singularity? Now, the solution is still singular, but the singularity is milder in 10 dimensions than in 5 dimensions. So if, and the structure of the singularity is different depending on this, whether this integration constant is strictly less than C1 or equal to, or C1 is equal to C2. So in one case, there is only a ring singularity in the internal space, and the other case is both a radial singularity and an angular singularity. But quite intriguingly, if one looks in different conformal frames, the metric can be arranged to be almost completely non-singular. So in this case, for example, there is only singularity at one point on the S5, and it's regular everywhere else. And in the other case, you can remove the angular singularity. Okay, so just a couple of minutes, I'm almost done. So we also computed the near boundary expansion for all fields to splitting order and found agreement with partial results of Friedman and Minahan. Then we checked the boundary conditions we have in 10 dimensions, the so-called normalizable modes. It's exactly the same with Puczynski-Strassler, once on matches conventions and so on. However, the splitting terms are different, and this implies that Puczynski-Strassler configuration does not solve the type 2B equations of motion, which is clearly not the same, and I'm not quite sure what to say about the validity of that work. So what is next? So we checked explicitly the type 2B equations that hold the generic points, but they could be still brane sources, and that's more complicated to do because this relies on understanding how delta function sources appear. So to diagnose for possible delta function sources, one may integrate the equations against test functions, and this is still ongoing. So there are definitely no 5 or 5 branes localized away from the position of the 5-dimensional singularity, but it's still open. There may be branes localized at the position of the 5D singularity. That's the current status. So now let me quickly summarize. So in the first part, I discuss classification of n deformations of n equals 4 Young mills that can be studied holographically. And we discuss how to obtain the supergravity potentials for single scalar sectors directly from the quantum field theory. Clearly, I just did the most simple case. It would be interesting to extend this discussion to other cases where the quantum field theory dynamics are understood. For instance, for the gauge kinetic function using Dirac-Alpha technology and so on. As I said earlier, these results suggest existence of single scalar truncations for massive modes, which seems very surprising from the supergravity perspective. And I focus here on the d equals 4, but the discussion straightforwardly extends to other cases. For example, the potential for d equals 3, delta equals 1 or 2 already appeared before in the literature. And finally, one slide about the uplift. So we discussed the uplift of GPPZ to 10 dimensions. It's still not clear whether the solution is sensible, and if it is, what it describes. Clearly, we need to compute more observables. For example, one can use the method of Kaluza-Klein holography to extract expectation values of high-dimensional Carrier primaries, which should help us decide which vacuum it is, and then compare this with quantum field theory expectations. And we hope to do this in the future. Thank you.
We are short on time, but let's have one quick question. So,
I missed the bit about why there should be a consistent truncation for the example you gave. Couldn't it just be a 10-dimensional solution?
Because the dynamic says that the scalar does not mix with anything else. And then this implies that, so in a sense, consistent truncations means that the dynamics on the quantum field theory side closes among itself. And this is a case where that scalar does not need to mix with anything else.